Okay, this is Dr. Hawkins again. Continuing on with my intro to transistors. I've already drawn a few things on the screen here. On the left is a depiction of what the transistor looks like internally. It's a P region for an NPN transistor anyway. It's a P region sandwiched in between two N regions. Now notice a couple of things. First of all, the P region is much thinner than the N regions. The N region corresponding to the collector and the P region corresponding to the base. That's these. Whoops. 1, 2. That's these regions here. This is the collector. This is the base. This is the emitter. The collector N region and the base P region are fairly lightly doped. That means they don't have very many impurities and therefore not too many charge carriers as compared to the emitter anyway. So let's mark that on here. It shouldn't show. Lightly doped. Lightly doped. And the emitter region, by contrast, is more heavily doped. It has lots of carriers. Now, the normal operating area for a transistor is when the base emitter junction, notice there's two p-n junctions, so it's kind of like two diodes. The base emitter junction is forward biased, so that means it's going to drop 0.7 of a volt, just like a regular diode. But the collector base p-n junction is reverse biased. That's the normal operator. We call that the active region for the transistor. When that condition occurs, there's going to be a flow of electrons from the emitter to the base naturally because that junction is forward biased. This is electron flow current. But typically, the collector supply is a much larger voltage than the base supply. All the base really has to have is 0.7 of a volt to forward bias the base emitter junction. So once the electrons start flowing, once this larger, and notice this is a larger depletion region here, the red lines signify my p-n junctions. The blue shaded area represents the depletion region. Now, because the emitter region is more heavily doped, I have a wider depletion region for this p-n junction here than I do for the other one with the collector base junction. So once I get the current started flowing through that forward bias base emitter junction, the positively charge of the collector supply here is much larger than the positive charge on the base supply, and it starts to pull electrons away, and it actually pulls more electrons than the base current does. So I get a bigger flow here. That is my collector current. And it works out that the more I make my base current, the bigger I make it, the bigger that collector current gets, and vice versa. And it's a lot bigger, not just a little bit. Turns out there is a constant for a particular transistor we call the DC forward current gain. And we use the Greek letter beta to represent that. D current gain. running out of room to write stuff, so I'll start a new page in a minute, but I don't want to leave this one quite yet. Beta is on the order of 100. It typically can range from, say, 50 to 150, maybe 200. And it's different for different transistors. If you don't know what beta is for a particular transistor, we normally just assume it's 100 just to give us a ballpark. And that's the number we'll use most of the time in this class. Beta is 100. So what that says is, now we'll go to the next slide. Collector current, when we're in that active region I mentioned, you got to have the base emitter junction forward bias and the base collector junction reverse biased. That's where this kicks in. IC equals beta IB. So if beta is 100, let's say, and let's let IB be 1 milliamp, I put 1 milliamp into the base, I get a collector current 100 times that. There's really 4 regions of operation we can have in a transistor. Let's see, now we'll do this. Let's go ahead and start a new page. I know I didn't put much on this one. Just give me room to play here. If we plot collector current versus VCE, the voltage between the collector and the emitter. And let's say this is 0, and this is maybe 5, 10, 15, we'll go to 20. And we'll let this be let's let this be 50, say, and 100, and 50, and so on. These are milliamps. It's probably too big of steps. Anyway, for each base current that comes along, we can draw a new curve. There's going to be a curve for IB equals 0. And it's going to be right here on the bottom. There'll be a curve. That would be, if beta is 100, that's half a milliamp. Puts me at 100 times half a milliamp is 50 milliamps. This would be 1 milliamp. This would be 1.5, 200, and so on. So that's a family of curves, we call it. And I didn't draw the last one very well. This is really going to go pretty much straight up until it kicks in. The bottom line here where IB is 0, we call that the cutoff region. The vertical part right here, we call that the saturation region. Now this is the region where the base emitter junction is forward biased, and so is the base collector junction. There's not enough voltage to put it in reverse bias anyway. That's the saturation region. And so this beta equals IB doesn't apply in that region. Where that does apply is in this broad region here. We call that the active region. Notice here that as VCE changes, the collector current doesn't change. It stays flat for a particular base current. So that says the base current is what's controlling the collector current in that region. Now there actually is a fourth region. In the active region, I think I already said this, in the active region, BE junction is forward bias and BC is reverse. And that's the region we have to be in for the transistor to operate. In saturation, they're both forward biased, and cutoff, neither one's forward biased. The transistor, there's nothing to forward bias the base emitter junction, so there's no current flow. Now there is a fourth region. Remember, we had breakdown for diodes, and the collector base junction is essentially a diode. It can go into breakdown. So the breakdown region, when it just takes off up that way again. Now we don't normally draw that on these curves because we don't allow that to happen. But it is possible if you overdrive a transistor enough, put enough voltage on the collector, it can break down. Now, we're talking about two diodes here. You cannot build a transistor out of two diodes. It doesn't work. That would look like this. I mean, they'll work as two diodes, but they will not work as a transistor. What it is like is if I have two diodes that share a P region. I mean, they're integrally part of each other. They're not just connected together with a piece of wire or a circuit board. They are integrally part of each other. So there's overlap there between them. So you cannot build that out of two distinct diodes. You have to build it as a transistor to begin with. Now, if I open circuit the collector, don't connect it to anything, then I could use the base emitter junction as a diode if I wanted to. And it'll behave just like any other diode. I can do the same thing with the base collector junction if the emitter's left open. There's usually no reason to do that. I mean, we have diodes. If we want a diode, we just use a diode. But we could do that if we really wanted to. Now, again, our ultimate goal here is going to be to amplify a small AC signal. And I've got one more little section here I want to do today to finish out at least the DC part of transistors. So let me, this is 15 minutes. I'm going to go ahead and cut this one off at 15, and I'm going to start a new one and finish this out to keep it from running too long. So I'll see you back shortly.